Hi folks, welcome to the YouTube live session for quantitative skills and reasoning. Today we're going to be talking about mostly statistics, so you'll see some mean, median, 5-number summaries, box plots, individuals, variables, and a whole slew of other things along the way. But I just wanted to kind of give you a review of that material from the statistics section of the course. So without further ado, we'll get started, and if you have any questions along the way, over on the side you'll see a chat box, so just go ahead and ask them in terms of the problems. And then remember, there's always a YouTube live discussion board you can post in there, and then I'll try and set up another discussion or review session later on based on those discussion postings. So without further ado, let's get started. We have a nurse rotates between maternity wards in 2 different hospitals, and during one shift at Healing Hospital and one shift at Healthy Hospital, she records the following weights of newborn babies. So at Healing Hospital, she recorded the weights being at 6.7 pounds, 7.5 pounds, 8.1 pounds, 8.6 pounds, 8.8 pounds, 9.0 pounds, and 9.1 pounds. Now at Healthy Hospital, we had 5.9 pounds, 6.6 pounds, 7.0 pounds, 7.2 pounds, 7.7 pounds, 8.0 pounds, and 8.5 pounds being those recorded weights. We want to find the mean and median of each data set. Okay, so the notation, we'll start with the mean because that's probably the more familiar, is usually X bar for the mean. Now, just to distinguish between the two, I'll put as a subscript the type of hospital. So X bar for Healing. Well, what do? Well, all we need to do is actually add up all the values of the weights. So 6.7 plus 7.5 plus 8.1 plus 8.6 plus 8.8 plus 9.0 plus 9.1. And then we need to divide by the number of observations included in there. So the number of observations, if you notice, there's 1, 2, 3, 4, 5, 6, 7. So we're going to divide by that 7. Now if you add all those up, what do we get? I think we get 57.8, I believe. Is that about right? You might want to double check me on that. But so we get 57.8, and then if you take that number and divide it by 7, you should get approximately, we'll round a few decimal places, so you get 8 let's say 257, and then that should be pounds. Okay? Any questions on that? And as I said, if you have questions, there's a chat box right there. Please feel free to use that, and I'll try and answer those questions if you see something you don't quite understand. So now on the next part, for Healthy Hospital, we want to figure out that mean. Once again, we use that X bar to denote the mean, so it's just a shorthand notation in mathematics for the mean. And then I'm using Healthy as a subscript to distinguish between the two. The process is pretty much the same. So we're going to take the values of the Healthy Hospital now. So we're going to take the 5.9 plus 6.6 plus 7.0 plus 7.2 plus 7.7 plus 8.0 plus 8.5, and then we take all that and divide by 7 once again, because there's 7 observations if you can count, and it lines up with the Healing. All the numbers do, so you can tell there's going to be 7 as well for that part. So what does that make? Well, that makes, let's add that up. I think that's 50.9 divided by 7. Once again, double check me there. So 50.9 divided by 7, and you get approximately, I'd say, 7.271 pounds. And don't worry if you can't do this in your head, you can use a calculator. It's the big thing on the calculator. What I'd suggest is just make sure your whole numerator is in parentheses. So I'll put parentheses around there just so you can see that. That's the biggest mistake I see in the calculator. People forget about the order of operations, so they forget to put parentheses around the whole numerator. So as long as you keep track of that, you're good to go, and that should hopefully be a little bit straightforward. If you wanted to do the extra step like I did, write down the 57.8 is the sum of the top, and then 50.9 is the sum of the top. That'll save you from that headache of hitting divide by 7 and getting an incorrect answer. So kind of keep in mind the range. Your mean should fall within the range of values too. So if you ever get a mean outside of the range of values, you've probably done something wrong along the way. Okay, so moving on to the median. We'll have two medians. So we'll do the median of healthy or healing first. So in order to do that, we need to find the location of the median. And I'll write that up here. Location of the median. And the place you can find the location is just take the number of observations plus 1 and divide by 2. Well, our number of observations in both cases are 7. So you go 7 plus 1 divided by 2. That tells us it'll be the middle number will be located in the 4th position. So all we need to do is count. And then the other little side note here, you need to make sure the numbers are in increasing order. So that should be the first step here. But notice we have in both cases, these are in increasing order for each hospital. So you have 6.7, 7.5, 8.1, and 8.6. So the 4th position in the first one is 8.6, and then the 4th position and the second one is 7.2. So the median for the healing hospital will be 8.6 pounds. Right? All we needed to do was find that position, and just once we found that, we were good to go. And the median for the healthy hospital was 7.2 pounds. Big thing there, just make sure they're in increasing order, and then once you have that and have the position, you're good to go. Questions on that piece? Okay, I don't see any questions. So at the bottom of the page, there's a second part, and so I'll kind of write this right within these margins here. Okay. So give the 5-number summary and draw a box plot for each of the 2 data sets. Okay, so we can do that. Not a big deal. So first off, 5-number summary. We'll do healing hospital first. So healing hospital, we need to write a 5-number summary. What does that consist of? Now, I won't write it for the second one, but you'll need to learn it. You have the minimum. You have the first quartile. You have the median, you have the 3rd quartile, and then you have the maximum. Okay, from this, right away, every time, if you have it in increasing order, the minimum and maximum should be your easiest. So if you look, the 6.7, that's going to be your min. The 9.1 will be your max. Okay, so the min and max, we're good to go there. Now the minimum we'll write down 6.7 pounds. The maximum we had 9.1 pounds. Okay, median we already had from the healing hospital. Just look up one step above, and we had 8.6 pounds. Remember, it's just the middle number. Now Q1 and Q3. So here's how we go about doing that. Q1, okay, we have to write a new list, and that list is formed by numbers to the left of the median. So our list is 6.7, 7.5, and 8.1. Okay, for Q3, we're going to write the numbers to the right of the median. So you get 8.8, 9.0, and 9.1. Now the location, in this case, notice we only have 3 values in our data set. So you go 3 plus 1 over 2. So and let me write location of the location of the median of the data sets will represent Q1 and Q3 once you write those down. So the median of those data sets is 2. So notice the values we get for Q1 and Q3 are 7.5 and 9.0. So 7.5 pounds and then 9.0 pounds. And there's your data set. You're good to go. Okay, so now on the next bit, let's do healthy hospital. So healthy, well, I'll actually write out what the values represent. So we go minimum, and usually you write these in increasing order. That's what you're trying to do. So the minimum is 5.9. So you have 5.9 pounds. Q1 we'll come back to in just a minute. The median we just had, and that's 7.2 pounds. Q3 we'll come back to in just a minute. And then the max can be found in that last position, so we found 5.9 and then 8.5 pounds. Okay, so now Q1, we got a new data set. Notice since we have 7 values, it's still going to be 3. Let me adjust this just slightly. I'll put this in pink so we can distinguish between the two. So now the new data set, remember we have that middle number, so we got to look at the numbers to the left. So our numbers are 5.9, 6.6, and 7.0 for the Q1. And we need to find the median of those. And then the numbers to the right, which will correspond to Q3, are 7.7, 8.0, and 8.5. And by the way, this isn't the only method for calculating these quartiles. You can also use percentiles. The calculation just might be a little bit more time consuming when you have such a small data set. So, and if you're using software, I mean, it's kind of up to the program, whatever that's using too. So I've seen both methods being used. Alright, so Q1, in this case the middle number, remember second number in that list, so that's going to be 6.6 pounds. And then the other case will be 8.0 pounds. So now the fun part, we have the 5-number summary of both of those. We want to create a box plot. So the box plot, the real fun begins, and let me get rid of that location business real quick so I have some room here. Alright. Okay, so taking a look at this, what do we actually need? Well, we just need to find some labels that are convenient for us. And so we can start at any position we really want to. That's the confusing part. Most people think you have to be 0 on a box plot. You don't. So what we can do is we can start at, I'd say, what is the lowest? 5.9 is the min. So we could start it at 5 if we want. And we can have each little hash mark. So that could be 5.5, this could be 6.0, 6.5, 7.0, and then we don't have to mark every one, but 7.5, 8, 8.5, and 9. And then we need to go up to 9.1, so we'll go right there. Okay. So now I'm actually going to use some different colors just so you can distinguish this a little bit. So the first one we'll do is we'll do healing hospital. Okay, so hopefully we can see that just fine. So with the healing hospital, what's happening? Well, we start at 6.7 pounds. Okay, so that's going to be somewhere right in here. Don't let your eyes fool you, that's a straight line. And that's going to be 1 whisker, and then the 9.1 pounds, so notice this is 9, well, let's see, 7.5, 8, here, I'll write them in. And that's the key. You have some freedom in this case where it's not made for you. 8.5, 9.0, and 9.5. Okay, so 9.1 would be something like right there. Now the fun part is we need to create a box around Q1 and Q3. So I'll do that in red. And usually that's where you start at. I'll start the next one, this part. So you go 9.0 to 7.5. So you have 7.5 right on the line there, and then 9.0. We're creating a box here. Now the whisker goes from the box to those positions of max and min. Okay, so 1 whisker is real small, 1 whisker is real big. But then we want a median of 8.6, so that's just above the 8.5 mark. And then what we do in that middle, that is our median. So everything is marked by our box plot. That's the whole trick to this. We're trying to mark every single pertinent piece of information from our 5-number summary. In our second case, I'm actually going to start with the box and show you how that goes. So we can go Q1 is 6.6. So this next one will be healthy hospital. So our Q1 is 6.6. So we want maybe right about here. Whoops. And then we go up to 8.0. We draw a box. Okay, now we have 7.2 is the median, so we find 7 and then we put the 0.2. Sorry for being kind of sloppy there. I'm trying to draw this, the surface gets a little slick on this, so you might not see the most perfect straight line ever. But so now for 8.5 we have as our top value. We'll draw that right up here. And you can always use the same color. I'm just trying to distinguish this so you can see from low to high what's going on. Okay. So there's our box plot. Now, even though these look quite different, from each quartile, you're talking the same percentage of data values. That's the funny part. This is representing percentages along the way. So keep that in mind. We'll come back to this a little bit later, but we're working with percentages is what's happening when we're doing the box plot. So it's giving us a way to look at those percentages. All right, so I don't see any questions on this first one. That's good. So we'll move on to the second one. And this tends to trip up some people, but we're dealing with normal distributions. So the body mass indices of American men between ages 30 and 50 are normally distributed with a mean of 26.2 and a standard deviation of 4.7. And then it says several health organizations have declared that men with a BMI below 18.5 are considered underweight. What percentage of American men are underweight? So this is a normal distribution, and the way you can tell it, it says normally distributed. So what we have here is a nice old bell curve. And now I'm going to try and convert to the standard normal distribution. And how do we do that? Well, the standard normal distribution has 0 as its center point, right? And the way we convert those things is to get a z-score. That is the trick to all these problems. And the z-score, if you recall, it's x stands for an observation, not the mean now. Mu stands for the population mean and divided by sigma. So in this case, what do we have? We have 18.5 is where we're considered underweight. We have, so x equals 18.5. That's the data value that we're concerned with. So now it might be tricky. Which one is the mean? So mu, it says a mean of 26.2. So that's going to be 26.2 for that. And then our standard deviation, which is sigma, is going to be 4.7. So in our case, we have x minus mu divided by sigma. So we have 18.5 minus 26.2 all divided by 4.7. Make sure to put that numerator in parentheses when you're doing this. And then you should get, we only need to round to hundredths when we look at our table. So I'll go negative 1.6. It goes 1.6383, but this will make negative 1.64 in that case is a closer number, I believe. So taking a look at that, what do we have here? Well, now we need to use the table for normal distributions, because what's happened is this says, okay, somewhere in here we have this data value negative 1.64 on our standard normal distribution. We want to find this area shaded to the left, and that's where we have this wonderful table that does all the work for us. Okay, and so that table, I'm going to try and bring it up here real quick. There we go. You can kind of see right here. And now we want negative 1.64. So what we do is first, there's the negative z-scores over on this side. And so we go to negative 1.6, and hopefully you can kind of see that. lined up right there. And then we go over, that's negative 1.60, this is negative 1.61, this is negative 1.62, this is negative 1.63, and this is negative 1.64, which says 0.0505. Okay, so taking a look at that. So we have our answer was 0.0505, but it's asked for what percentage? And so that is the same thing as 5.05%. Okay? Whole trick was setting up the z-score and then just looking up in the table. Now for our second problem, we're going to do more of the same. And I'll try and fit that right in over here. So in this case, though, we have x equals 30, and then our mu and sigma have not changed whatsoever. So mu is 26.2, sigma equals 4.7. So our z-score equals 30 minus 26.2, all divided by 4.7. And when you round that, what do we get? We should get 0.81. So 0.81 as our z-score, because it's 0.8085, I believe, is what it comes to, but we only need to round to the nearest hundredth. All right, so now here's the difference. We have 30 or, so men with a BMI of 30 or greater are considered obese. What percentage of men are obese? When taking a look at this, we still have our normal distribution. 0 is the middle point. But now we have something like this. Okay, so here's our 0.81, right? We want to shade, since we're greater, we're going to shade to this side. Whereas before, when we shaded in, what we found was this area was 0.0505 or 5.05%. That meant that this other side would be 1 minus 0.0505, because the whole area makes up 1 or 100%. Okay, that's the tricky part to this, is what's going on in terms of percentages, kind of giving you a visualization as to what's going on. Now, so we'll find this corresponding value, but we'll need to go, in this case, that value will correspond to this side, and this would be 1 minus whatever that answer is. So we'll go 1 minus whatever our answer is in that chart. So we're looking for 0.81. Okay, so 0.81, let's take a look here real quick. And so when we slide this over, here's our z-scores with positive values. We have 0.8, you have 0, and then you have 1. 0.81 is 0.7910 as our corresponding value. And so you can kind of see it right in our chart there. I tried to open up a new tab there, it looks like. But so 0.7910, oops, come on. There we go. Okay, so we have 1 minus 0.7910 because that area to the left was 0.7910. So 1 minus 0.7910. So what does that make all of a sudden? Well, that makes 0.209. But once again, we wanted a percentage. So what percentage? So our answer for this would be 20.9%. Questions on the normal distribution and how to work it. The main key that you need to focus on is trying to get that z-score. So if you're given a percentage and trying to look for a data value, you can still do it. You need to find a z-score and then work your way backwards. It's just using a formula there too. But everything with normal distribution is try and get a z-score however you can. Okay? As long as you do that, you're going to be in pretty good shape for the rest of the way. Alright, so moving forward, determine whether the data described are qualitative or quantitative variables, is what it's supposed to say. And if the variable is quantitative, determine if the data is discrete or continuous. In both cases, qualitative or quantitative, state an example of a graph that could be used to help display the data. Okay, so our first one, variables, right? We want to first figure out what the heck is the variable. Okay. So we have the weights of a subject. So that right there is the variable. Now think about it. Is it a numerical variable or is it a categorical variable? Well, when you think of weights, you're thinking like if we're talking weights of a subject, you could be 100 pounds, we could be 200 pounds, 150 pounds, all sorts of all over the place, 300 pounds, whatever the case may be. But those are all numbers, and they're not numbers in terms of a ranking system like, rate how you feel, or on a scale of 1 to 5. They're numbers in terms of, they could even be like 150.78, right? Those are all possible values, and they're numerical values, so that tells us this is a quantitative variable. So we have a quantitative variable. Now, so since it's quantitative, we got to determine, is it discrete or is it continuous? Okay, well, let's think about it. Weight, as we mentioned before, does it stop at a number, or can we keep on going more and more precise? So for example, would 150.7 pounds be a valid answer? Well, yes, it could. Could 150.9 pounds be an answer? Yes. Could 200.3785968 pounds be an example? Yes, it can. All of those are valid numbers for the weight. Since there's no gaps, we could go as far as we want in terms of the precision. That means that we have a continuous variable. So quantitative, we have continuous for our variable there. And so now the next part, what type of graph? So the graph possibilities are actually kind of given to us. Really, there's only two types of graphs that deal with, well, there's more to it, but in this class there's only two types of graphs we really focused on with that, and that's a histogram and a stem and leaf diagram, or other ways we can say that is stem plot, right? And so that's the same thing as a stem and leaf. Because those are the observations that deal with numbers. This trips up a lot of people. A lot of people think of a histogram as a bar graph. It is not, because a histogram has a quantitative variable on the x-axis. That's the big difference, okay? Versus a bar graph has categories. So keep that in mind when you're doing this. Okay, so next one, the color of new cars. The color is actually our variable, right? So what's that telling us? Well, since we have color, think of what are our possibilities. Well, black, blue, green, yellow, burnt sienna, you name it, you can have some color going on there, but that's a category. That is not a number whatsoever. So since it's a category, that tells us this is qualitative data. And since it's qualitative, we don't even need to discuss continuous or discrete, because those are dealing with numbers. Okay, so now we have a qualitative. What are our graph possibilities? Well, and we only need to list one, but I just want to kind of make sure we're on the same page. So this is the case where we can use a bar graph. That's actually our better option. And another one would be a pie chart, right? Those are pretty common, what you see there. So hopefully that makes sense in terms of what we've been dealing with in here in our class. But make sure you can distinguish. The big trick is histograms and bar graphs. A lot of people think they're the same thing. They're not. It's the type of variable that you're using it with. Quantitative variables deal with histograms. Qualitative variables deal with bar graphs. Make sure you can distinguish between those two parts. Okay. So moving forward, now some fun stuff in terms of correlation. Make sure, the big thing that I'd like you to take home though, a lot of mistakes are made, and I see it in the news all the time. People mistake correlation for causation. That is not the case, right? So you should not have correlation and causation do not mean the same thing. And the big one that I like is they talked about as ice cream increased, so did the cases of polio or and whatnot. That's one of the videos you got to see. So, and we saw, hey, it happened because of summertime, more people could get infected. That turned out to be the real reason. But people start to think of some crazy things, and they might be correlated, but that does not mean causation whatsoever. Okay, so always keep that in mind when dealing with correlation and causation. All right, so we want to make a scatter plot for this thing. Now you actually have some options, and just make sure you're labeling it accordingly. So you can do X and Y's however you want, because it doesn't say one causes the other. So the table below gives the 2012 per capita gross domestic product and the per capita spending on defense for 8 developed countries. So we have the 8 countries are Australia, China, France, Germany, Japan, Russia, United Kingdom, and the United States. So our per capita GDP, we have 65,220 for Australia. The per capita defense is 1,174. And then you can go on down the line, 5,320 for the per capita GDP, and then per capita defense is 106 for China. In terms of a good labeling system, notice that you have to have a feel for what's the lowest and what's the highest. So here's our lowest on the per capita GDP, and then so this is the low, and then what's our high? Well, we have 65,220, so that's the max. Okay, and then when you look at the per capita defense, the low or the min goes right there, and then the max would be good old US of A down there. Okay, so when we're doing this, you can kind of get your scaling in place. So because we're going to make an X and Y axis, and there is no causation distinguished here, so you have some freedom. So that means we'll put per capita GDP on our x-axis, and then this is per capita, and so this is in dollars, and then per capita defense. Okay. Now you have some stuff that can do this for you, but you will often have to change the bin widths, and what I mean by bin widths, the tick marks along the way, and you'll have to get a good idea for scaling, how to scale this graph, and that's what I want you to be aware of. So notice we raised to 2,250, so let's maybe make it 2,500. Oh, I'm putting that on the wrong scale. I should pay a little bit closer to attention there. So we'll put 2,500 on that Y scale. On the other case, when looking at the per capita GDP, we need to go all the way up to 65,220. So let's just call this 70,000 over here. So that means we probably want 7 tick marks would probably be pretty good. 10,000 apiece, 1 evenly spaced, 2, 3, 4, 5. I probably should scoot this 70,000 over a little bit and space it out perfectly. And don't let your eyes fool you, these are evenly spaced, right? So, and this is going to be 10,000 for each tick mark. 20,000, you get the idea there. So if we have 2,500 on the other scale, we'll do 5 of those. So oops, 2,500. Let me do this. I'll raise it up one more. There we go. All right. So now, just so you can see, I'm actually going to use initials along the way, alongside of the dots that we'll use. So Australia, we have 65,220 is the per capita GDP. Okay, so it's going to be way over on that one side, and then the per capita defense is 1,174. And remember, this is 500, 1,000, 1,500, 2,000. All right, so 65,000, 1,174. So we get something like that. Okay, and this would be A for Australia. So that one's checked off. China, 5,320 and 106. So 106 and 5,320 would be something like right here. And so we have China going right there. All right, so France, 42,420 and 955. So 42,000, so that's 30, 40, 42, and 955 will be something like right here, because 40,000 is right here, and that would be good old France. All right, now, so Germany, 43,573, and so Germany would be maybe right in here. Japan, 46,465. Ooh, that's really close. So I'll put another dot just so we can distinguish. And Japan will probably be, whoa, didn't mean to do that. Japan is right about there. Okay, Russia, 13,290 and then 504. So 13,290 and 504. So you're right about there for Russia. The UK, so we have 1,000 and 38,100. So 1,000. That's the UK. And then the good old US of A, so that would be 47,470. And then we want, 2250. So we'll go right about here. Now, taking a look at this, you might say, oh, well, this seems like no correlation, but if you look, if I were to draw a line, granted, I have some below and some above, but the general trend seems to be going up. As one increases, the other increases, the exception being Germany and Japan, right? But so a majority of these tend to be doing that. So in terms of our next question, state whether the variables appear to be correlated. And if so, state whether the correlation is positive, negative, strong, or weak. So although it's definitely not a strong correlation, it's a weak correlation because we have numbers kind of spread out all over the place. It's not corresponding to that line, but a weak, but we do have a positive correlation. It seems like it's trending up. But remember that correlation is weak in comparison. So, and that's the whole thing. We can have positive, but it just might not be as strong as we like. And you're going to see that happen more often, right? Especially as we add in more data. If we add it in a lot more countries, you can start to see more of a trend and whatnot. So hopefully that gives you an idea, though, what we're looking for. Weak, positive, negative. So negative would be a downsloping line if we were to draw one. Kind of keep that in mind when we're trying to approximate with a line. So, and you're going to get in, if you actually take a statistics class, you get into how to calculate these lines rather than just trying to approximate it and limit the errors. So, but it gives you an overall understanding. The main thing I want you to do is make sure you understand correlation does not imply causation. All right, so our next one. A random sample of 10 Gulfstream employees were asked how many sick days they used during the past 3 months. The responses were 0241370100012. State the individuals in the above data collection. So it's the information that we're gathering from what people, or in this case people, but in some cases what thing we're gathering the data from. And in this case, random sample, we gathered this data from the Gulfstream employees. So in terms of the individuals, that is what we're looking at. The Gulfstream employees. You could even advance it. Gulfstream employees asked about their number of sick days used. Now, we want to state the variable, and we want to determine if it's qualitative or quantitative. And if it's quantitative, determine whether it's discrete or continuous. Okay, so when we take a look at this, what are we dealing with? Well, the variable, first off, what is the thing that's changing? It's the number of, and let me actually write it out, number of sick days used. During the past 3 months. Now, is this variable quantitative or qualitative? Well, you see right there, they give you the data set. It's all numbers, right? And it's that many days. So in this terminology, that tells us it's a quantitative variable. Now we have to determine if it's discrete or continuous. This one can play a little bit of tricks on people, but think about it. Are there gaps in between the numbers? Well, I would claim that in this case you're only claiming a whole day at a time. Maybe you could even claim a half day or a quarter day. You could get down there, but you still have a gap. You couldn't say, oh, I want to claim 0.00133579 days. No, it isn't going to allow that to happen, right? You don't have systems in place for that. So the quantitative variable in this case, we have gaps, so we are dealing with a discrete variable. Okay, so hopefully that makes sense in terms of this one. Remember, part B is right here. And then, oh, by the way, if you were to draw a graph, histogram, stem plot, probably a stem plot would be your best, or stem and leaf diagram, if it's this size in terms of number of people. So, yeah, hopefully that makes sense on that one. If you have questions, once again, there is a chat box. Please let me know. So for our next one, we want to make frequency tables for the following data set. Include columns for relative frequency, cumulative frequency, a website that reviews, and so we have here a website that reviews recent movies, lists 5-star films, the highest rating, 5 5-star films. Then we have 10 4-star films, 20 3-star films, 15 2-star films, and 5 1-star films. Okay, so our data set here, our first scenario is a 5 5-star films. Okay, and let me actually do right up above it. We'll do frequency. I know it calls for relative frequency next, but I'll do cumulative frequency just because that'll be the easiest of the bunch. Next to frequency. And then we'll do relative frequency. And then I'll also claim how to do I'll tell you how to do cumulative relative frequency if it's ever asked of you. Okay, so 5-star films, and then we have 4-star films is our next category. And then 3-star films. Two-star films. And then 1-star films. Frequency. Okay, website that reviews the recent movies list 5 5-star films. So that means our frequency of the 5-star films, that means we have 5 of those 5 stars. Okay. So actually, if we were to list out this data set, by the way, what is this telling you? It tells you if these are the number of stars I'm writing down. So we have 5 of the 5 stars. Now the next part would say 10 of the 4-star films. So that means we have 10 4. So you'd have something like this. 1, 2, 3, 4. And then me having to write out a data set of all these values, right? And then you can continue on down, right? The next one, you have a 3-star film. So 3, and then there's a whole bunch. In fact, we know how many. There's 20 of these by just reading that information. So a lot of people confuse. They think the data is 5, 10, 20. No, the actual data values are 5, 4, 5, 5, 5, 5, 5, 4, 4, 4, 4, 4, so on and so forth. So if you're finding an average rating, things like that, that's how you use this. So when you see that sort of summary. So our next bit, 15 2-star films, and then last but not least, we have 5 1-star films. Okay. So that one's hunky-dory. So now the next part is cumulative frequency. So what does the word cumulative mean? Cumulative means sum. And so that's all we're doing, is we're taking the sum, and so let me do this for the next row. So what goes in this row is the sum of these two rows, right? So that would be 5 plus 10, and so I'll write it up here as 5 plus 10. But then our actual answer, that should be an entry here, is 15. In our next row, we should do the sum of the 3. So it should be 5 plus 10. Well, if you notice, it's take 15 plus 35, because 35 is the sum of the first 3 rows. So you get 50 for that entry. So it gets from 5 plus 10 plus 20 plus 15. Okay, and the last one we're going to add on 5 to that. And the nice thing about your last row, if you've done things correctly, it should always be your total. Now, when I'm putting those in though, we erase that little work. You can do the work on the outside, but that's what's happening all the time. So, and hopefully we can see that. So now that we have that information, I think we're ready to rock and roll with it. So we want to try and find the relative frequency. And the way we do that is by taking the number in the row and divide by the total. So this should be, one way to write it is 5 over 55, or another way for us to write it, this would be 9.1%. Okay. The next one, we would take 15 divided by the total of 55, so 15 over 55, and that is approximately 27.3%. Now, notice how we're rounding, so you might not get a complete whole answer. Keep that in mind when you're doing these. So that rounding causes a little bit of error that we run into. So in our next one, we have 63.6%. When we take 35 divided by 55, our next one would be 50 divided by 55, and so in that case we have, it should be like 90.9%. And then last but not least, we have 5 divided by 55, and that's once again 9.1%. If we were to do cumulative frequency, or cumulative relative frequency, I should say, all we're doing is summing up the percentages, because you take a sum, is what the cumulative stands for, so sum of the relative frequencies. So you take, like your second row would be 9.1% plus 27.3%, and there you go. Or an easier way would be to do 20 divided by 55, right? Okay, so hopefully that makes sense on how those work. If not, let me know. That's what I'm here for. So just ask questions away, and I'll try and answer them as best I can. So the next one, the following box plot portrays the resting heart rate of marathon runners that participated in the Savannah Rock and Roll Marathon. Determine the 5-number summary corresponding to this box plot. Remember that it corresponds to the minimum. And where can we get that information? Well, we take this line and draw it straight across, right to that number. Well, that number is 40. So our minimum equals 40. Our next number is Q1. Right? So Q1, we take that number and draw it straight across, and notice we get 52. Our next number is our median. Okay, so we take that value and draw it straight across. And sorry, my pen isn't drawing things so straight, but hopefully that seems to be going pretty well. So that number looks like, notice each one's jumping 2 at a time, so 2, 4, 6, so that's going to be 56. Their next number is Q3, so we just go to our box plot, draw our line straight on over. Whoa, got a little up high, but I recovered towards the end. Sorry for the sliding there. But 64, and notice you don't have to draw the number all the way to the side. If you can recognize it right away, that's fine as well. And then our maximum, so we're going to take that, and hopefully I can draw a straight enough line, and so that looks like 94. So maximum equals 94. Okay, and what is this resting heart rate? So this would, each of these are beats per minute. So beats per minute, beats per minute, beats per minute, and then beats per minute. Now the next part, determine the percentage of runners finishing between the first quartile and the median. So you might say, oh, I need to subtract and then I got to figure all that. No, you don't need to do that at all. Every time, regardless of how big that range is, how small that range is, that's 25%, because this is a 50% mark. This is a 25% mark. The Q3 is the 75% mark. And notice when you go to the maximum, you're at 100%. So you take 50% minus 25%. Our final answer is 25% there. Okay, questions on that? I don't see any, so I'll be rocking and rolling with the next bit. So for the following situation, state whether you expect the distribution to be symmetric, left skewed, or right skewed. Okay, so now you actually have some freedom here, and that's what I want you to realize. But the salaries of professional football players, if you made a good argument, either way, I'd kind of accept it here. But so what I would claim, if we had salaries, I would say a lump of these, if we started at, I have no idea what the minimum salary in the NFL is, but 500,000, and there's players making, so if we go 500,000, if we go 1 million, and then we go, let's do 2 times 10 to the 6, so 2 million, 3 million. I say what you're going to get most likely is a lot of data values right in this range. Right? But then there's these players, and if I extend this even further for you to see, even at 10 million, that doesn't, there's some players I think they're making like 40 million or so. I forget what the actual number is. But at the end of the day, let's say this is 40 times 10 to the 6, right? You're not going to get a large number of players out here. You might get, and if I had tick marks all the way throughout, whatever the case may be, most of your tick marks or most of your values are going to lie around here. You might have something like that, but then all of a sudden you're going to get this drop off because not a lot of players are making the multi-million dollar, like tens of millions of dollars and things like that. So you get a distribution that looks like this. Notice the tail. So if I were to draw a curve, I get a big hump, and then I get a tail like that. The tail is over here. So what does that tell us? It tells us our distribution is skewed right, or skewed to the right. Okay? So now for speeds of cars, how do we go about doing that on the road? Well, let's think about what's happening in those situations. So you might have, if we're on the highway, let's say 45 is the min, right? You go 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, right? So speeds of cars on a road where visible patrol car is using radar to detect speeds. So let's say the speed limit's 70 miles an hour or something around there. You could go through your own scenario. You might have quite a few right around there, right around here. There might even be a drop off, and there might be some over on this side. Something like this. And then there might even be a drop off where you have somebody driving 45, and you might have some people driving around 80. But what I'd say is those people driving 100 that blow off your doors, and you might be that person blowing off my doors, so I'm not driving 100 miles an hour in my vehicle, I'll tell you that much. But what this makes is you'll get a few people here and there, and there might not be any in that position, but over on that side that are speeding, right? And those are the people that get pulled over on the side of the road, unless you can outrace them, I guess. And what's happening to our curve? Well, once again, the tail is over here, right? And so this would be another situation of skew to the right. Now you can write a reasoning, right? So you could say, oh, I believe only a few people will get pulled over. And if you think a majority of people are getting pulled over on both ends, like maybe you might have this be symmetric, right? Because of you think people are going under the speed limit. I don't see that happen too often. Usually they're speeding. If that's the case, it's not under the speed limit on the freeway. And it doesn't distinguish in the problem where we're at, but you can get an idea of the types of scenarios that we're dealing with here. So, okay. Alright, so the next bit, true or false. If two data sets both have a mean of 73, then both data sets will have the same standard deviation. So let's take a look. I'm going to create two data sets, and I need to keep the mean to be 73. And so the way to do that, the first off bit, I'll just have every value be 73. And I can list 20 of these, 40 of these, doesn't matter how many. But notice this has the mean being 73, so x bar equals 73. And then I'll tell you right now the standard deviation, which we usually denote by S in this case, but I'll just write it out. Standard deviation, this one's an easy calculation, it equals 0. But set 2, I'm going to be a little bit crafty here. Okay, let's say I subtract 10 and 63, but then I add 10. So notice negative 10, positive 10 of this, that would cancel out and become 73 again. Okay, so next one I'll subtract 20 and I'll add 20. And then I'll subtract 30 and add 30. All of those sum up to basically give you 73 as the average. But the standard deviation is not equal 0, and I'll tell you why. Because when you take a difference just of one of them and square it, all of a sudden you get a positive number. And that positive number all of a sudden means that standard deviation is not going to be equal to 0. It doesn't even matter what it is, but it's not 0. Okay, and standard deviation is talking about the spread of this distribution, so that number will kind of indicate how this thing is spreading out from 73, spreading out from the mean. So that tells you right there, since we have the standard deviation, it's actually a bit greater than 0. That means that this statement's false. Okay, so make sure you can distinguish. Standard deviation is talking about the spread of a distribution. Mean is talking about is a measure of center of distribution. Okay, last but certainly not least, with the enthusiasm for statistics at an all-time high, students were found sprinting from their vehicle to the classroom just to be the first person to grab a seat. Times of the students were recorded in seconds and given in the stem plot below. Okay, so these represent what this is telling you. This is tens, and each of these are your ones place, right? So if you're looking at your data values, you have a data value that goes 13, 14, 15, 19, 19, and each of these are in seconds. So then you have 21, 27, 27, 28, and so on and so forth, right? If you need me to write it out, just let me know. Oh, okay. Yeah, if you want, I'll write it out. So you have 32, then 45, 49, 49, 62, and 62. Okay, so let's count the number of data values. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We want to find the median of this given data set. So the location of the median, well, remember we take the number of observations, which is 15, plus 1, and we divide by 2. So that should be in the 8th position. Now I can use it on this block over here, or I could just count from here. So 1, 2, 3, 4, 5, 6, 7, and 8. So that's going to be our magical number combined with that. So the median equals 27, and then this should be seconds. And that's it. So hopefully this gave you a little bit of insight into some of the statistics questions that you can be anticipating. Hopefully, if you have any other questions, there's always a YouTube live discussion board. Please feel free to ask those questions there. Wish you all the best of luck on that upcoming exam, and let me know if you have any other questions along the way. Okay, y'all have a good one.